Our next speaker, Professor Dr. Robert Pitz Paal, Director at the Institute of Solar Research, DLR, German Aerospace Center. Speaking on today's topic, CSP PV hybrid solution, base load, low-cost solar for grids, industry, and hydrogen. Over to you, Dr. Robert.
Yeah, good afternoon, ladies and gentlemen. Welcome also from my side. And this is a technical talk that will highlight a technical opportunity that comes up if you combine two solar technologies, photovoltaic, I'm sure everybody of you knows about, and concentrating solar power. And I would like to highlight what would be actually the benefit of combining both technologies in one system. Just to catch you up a bit with concentrating solar power, you know, this is the technology with concentrating sunlight and thermal energy storage. It is relatively young technologies. Overall in the world, about 6.2 gigawatt are operational. You see here the distribution around the world, mostly, of course, in Sunbelt countries, and there are also a lot of projects under development. Interesting to note is that this technology has undergone, like all other renewable technologies, a significant learning curve. And this is what you can see in this graph here. You see the cost of electricity in US dollars per kilowatt hour, and you see the deployment rate, the cumulative deployment rate for CSP in the left-hand side curve. You see it started in the year 2010, 2008, at a range of about 40 US dollar cents per kilowatt hour, and the costs have dropped by the implementation to about today, about 7 US dollar cents. And you see other technologies have even achieved lower costs. We know from PV that have reached 3 or even less cents per kilowatt hour in the overall implementation, but you see also at a much higher deployment rate. So there's a good chance that with more deployment of CSP, further cost reduction can be achieved. But even at today's cost, there's a very interesting idea about combining those two technologies. And well, one of the points is that CSP technology, although it's a smaller, I would call it the smaller brother of the photovoltaic, it has some potential in the global energy system, also in scenarios from the IA, for example, because of its characteristics of dispatchable power using a thermal energy storage. You see that the technology by the year 2040, depending on the scenario, may come up to a capacity of 250 gigawatt on a global scale, which would require an annual growth rate of more than 15 up to 25%. But beside this market development that we see in this technology, and there are some, let's say, estimations that by the year 2027, we will surpass 1.3 gigawatt annual installation rate at $7 billion. The more interesting question is what is actually the benefit in combining, let's say, these two different systems. And you all know photovoltaic power is very cheap. Electricity actually is cheap when the sun is shining. But in particular, if you want to run industrial systems, hydrogen production systems, it would be very good to have systems then that run for more full load hours, that run around the clock. And so storage solutions are required to satisfy actually the demand after sunset. Today, battery storage systems are still relatively expensive. In particular, if we think about very large power units with several hours of storage capacity, hundreds of gigawatt hours of storage capacity, this is actually a very expensive option still. And here, concentrating solar power offers actually a dispatchable solution by using the proven thermal storage. Thermal energy storage actually is an easy system that stores hot salt in a tank and can provide hundreds of gigawatt hours of storage capacity. In addition, CSP actually uses a conventional turbine. It provides ancillary services to the grid, so it offers some additional benefits to that. So combining both technologies actually offers both low cost and dispatchability, and how this can happen is maybe explained a bit more in the details. So the first question is, why actually is thermal storage so attractive to be integrated? And this can be maybe seen from this little animation I show you here. When we look to concentrating collectors, then at a good site, they provide high temperature heat to a conventional power cycle for about 2,000 hours a year. And if we would add a thermal energy storage, then we would actually also increase the solar field. So using twice as many collectors, providing twice as much heat to the system, and we would put part of the heat to the thermal energy storage and operate the power block for another 2,000 hours. You see, by adding more and more of these systems here, you could have a full load hour capacity of 4,000, 6,000, even more full load hours per year. So actually really helping to come to a kind of baseload operation that would be very suitable for powering industrial complexes or hydrogen production facilities. So the interesting thing is that the cost of electricity of the system with thermal energy storage is actually cheaper than the system without. And this has to do with the fact that this system produces twice as much electricity as the one without storage, but it doesn't have twice the cost because it only has twice the collectors, but not 2 times the power block. Only has a, as you can see here, relatively cheap thermal energy storage that needs to be added to the system. So when you look to the storage capacity and the relative electricity cost, then actually the lowest cost of electricity is achieved at a relatively high storage capacity in terms of full load hours. That would actually lead to a situation that you could run the system around the clock. So if you think about the combination of the two technologies, then you have 2 different characteristics. PV actually is cheapest with no storage. And then if you add storage, more and more costs go up because you have to pay extra for the batteries and so on. And with CSP, we have the characteristic that we saw in the previous curve, the lowest cost when the system actually runs around the clock, particularly around the clock. You see, there can be a situation that the CSP electricity actually is cheaper than the electricity from the PV and battery system. And in particular situations, it really makes sense to combine the both systems. And the PV system actually then runs during daytime, provides electricity during daytime, and the CSP actually over the nighttime. And this is beneficial, in particular under boundary conditions where a certain fraction of power demand is during nighttime, or a limit for the power feed to the grid is available at any time. So you need to shift some of your production to some other time, or in some cases, you have a time of delivery tariffs to favor nighttime production over the direct in-feed. So in those cases, it's worthwhile to consider, let's say, the combination of the 2 technologies and trying to shift and bridge the different systems. So to put it in more, let's say, in a graph, how this can work, you see here that you have electricity from photovoltaics, and during the daytime, it's not constant, actually, the production rate. But if you would cut off it at a certain fraction to provide a nominal output and take the rest of the PV electricity, also put it to the thermal energy storage, in addition to the energy that comes from the concentrating collectors, is this part of the curve here, the solar heat, then you could run your system during daytime at a constant nominal load and extend this operation during nighttime and the evening, even around the clock, by just taking the electricity from the grid. So it's a kind of balance of these 2 systems, and the storage size depends very much on the demand profile. And I just show you here a kind of optimization. That depends, of course, on many, many different parameters. But actually, the freedom in the system is if you have a certain power block capacity and a certain energy system, the freedom is the scaling factor of the solar PV field. So make the solar PV field bigger or smaller. And the other scaling factor is the size of the solar collector field that provides the energy, the heat to the system. The number of collector rows, we call them rows in the parabolic trough system. And you see here at a certain combination of these 2, in this case, is the red curve, you achieve the lowest cost of electricity. That in this particular case would lead to a combination of 225 megawatt PV and 60 megawatt CSP. as a system that actually provides the lowest cost of LEC if you want to cover a certain demand profile. This actually is interesting if you are talking about hydrogen production, because hydrogen production actually needs a constant load, because in that case you can scale down your electrolyzer. Your electrolyzer can produce actually the energy over more hours of the day. You can avoid expensive hydrogen storage systems, in particular also if you have downstream processes, that you have a kind of constant 24/7 operation with such a system. That would be possible by combining or by providing energy, renewable energy around the clock. The interesting thing is that CSP also can provide high temperature heat, not only electricity, and maybe in future designs of systems, when we are talking about future electrolyzer technology, high temperature electrolyzers that are more efficient, then also high temperature heat may be used to be integrated into such a concept. Let me try to explain in this graph what is actually the impact of the hydrogen production cost. Hydrogen production, of course, depends very much on the cost of the electricity, and you see here different graphs for different assumptions on the electricity cost, but also on the cost of the full load hours of the electrolyzer. You can see if you have for example, a PV system with low electricity cost, but only a limited number of full load hours, then your hydrogen production can be more expensive in the case that you have a bit more electricity, higher electricity cost, but higher number of full load hours. So it's very important to do, let's say, the detailed analysis. Depends very much on the boundary conditions, of course, also on the cost of the electrolyzer. But the idea to have a constant supply of electricity and maybe on heat in a complete chain of the production of fuels, also maybe synthetic fuels, not only hydrogen, is of a strong benefit. I would like to introduce to you a project that is followed by a German consortium. They want to go for a first pilot plant for producing methanol. Methanol, of course, needs hydrogen, and you need green hydrogen in this context with an electrolyzer. And of course, hydrogen may be also sold directly to the market as a part of the business model, in addition to selling oxygen as an additional source. But of course, the other part is where do you get your carbon from? And here, the idea is to combine it with a cement factory where you have intrinsic emissions of CO2 that can be integrated into such a system so that methanol can be generated. And all the systems should be powered by a CSP PV hybrid system, providing electricity to the different components here. And in addition, where necessary, also some high temperature heat to the concept. This is a project in preparation as a demonstration discussed with the German government right now. And if you're interested, I can provide you with industrial contacts on this project. So let me conclude with that. I hope that this presentation could show you that the combination of CSP and PV power plants offer the chance for cheap and dispatchable solar electricity and heat. We know, of course, that the combination is complex. There are, let's say, several optimization aspects, and there may be cases where just the one or the other technology is the only best solution. But in many cases, we assume that the combination actually leads to the lowest cost. And this depends, of course, very much on the cost of the subsystems, and they're all changing dynamically, like batteries, for example. So have to be careful in the analysis and update regularly. We at DLR have developed software tools that can help to find in pre-feasibility studies, let's say, the first best options for further development, for further investigation, and we're happy to cooperate on that. So with that, I finished. I'm happy to conclude, and thank you very much for your attention.
Thank you, Dr. Robert, for your presentation. So one question for you, which I have, is any particular Middle East country you have started with these projects anywhere?
Yeah, well, right now the most intensive discussions are going on with a collaboration with Tunisia, but this is just let's say kind of first approach. We have some concrete contacts there, but I think this is not something which is, let's say, very unique or special to Tunisia. I think this is a concept that would fit to several MENA or Arabian countries where you have the boundary conditions that are required, as I've shown in the presentation.
All right. So thank you for your time and presentation, and I hope to meet you in Oman next time.
Thank you very much, and have a good day.
Same to you, sir. Bye-bye.